Okay, this is our 0654 Summer 1941. We're looking at physics question number 6, the second of the physics questions. Probably gone a bit overkill here on some of the stuff, but why not? Let's first look at our electromagnetic spectrum here. You're given 3 parts of the spectrum here, and you are asked quite simply to write visible light in the correct part of the spectrum. Now you should be aware that visible light falls here. Okay, visible light is basically in the middle of our spectrum. Okay, now what I've done is I've written it in here, but I've also added the missing bits. Okay, you never know what you might be asked to do here. Okay, you're not asked in the question to add X-rays, infrared, or radio waves. However, I thought it's a really good one for you to have. A few things to think about here. X-rays are very similar to gamma rays. We've talked about gamma radiation. Okay, X-rays are also ionizing, which is why you are encouraged not to have too many X-rays in your lifetime. Okay, ultraviolet is next to visible, and infrared is also. Now this is where you need to think about your visible spectrum, because at one end of the spectrum, at the other end of the spectrum, we've got colors, right? The visible spectrum is all colors. At this end of the spectrum, we have violet. And you should know that the spectrum goes all the way from violet through to red. Oops, my pen's running out now. Okay, so please be aware that those names are very, very helpful to you if you were trying to add anything in about our spectrum. Infrared is next to red. Ultraviolet is next to violet. Okay, and at the end there we've got radio waves. What we're doing here is we're changing a couple of variables. Remember, these things all have the same speed. Okay, 3 times 10 to the 8 meters per second. Please don't write 330. 330 would be the speed of sound. Okay, as we're going down the table here, what we're doing is we are increasing the wavelength. We're going in the opposite direction. We are increasing the frequency. Okay, so this is these gamma rays are high frequency, low wavelength, and at the other end it's the opposite. We have low frequency, high wavelength. Okay, enough about that. Let's look at question B. We've got a train, and we are asked to suggest a value, and again, emphasis here being on suggest, okay, the speed of sound in water. Okay, so my estimate or suggestion would be 1,500. Point here is that in air is a gas. You're told the speed of sound in a solid, which is steel. Okay, so what we expect is that the speed of sound to be somewhere between the speed of sound in a gas and the speed of sound in a solid. Okay, so really any reasonable guess there would be okay. The idea being that we're somewhere between the two. Water's the liquid state, so the speed should be slower than in the solid, but faster than the gas state. And that really comes to do with our arrangement of the particles in the states. Remember, in the solid, we are close together. And in the gas, we are far apart. As sound travels as a vibration between those particles, the further apart, the slower it's going to be. Okay, this is a nice question. Quite a lot of work actually, this last one for the time difference, but really we're using the same equation each time, which is speed, distance, and time. Okay, D equal to V times T. Hopefully you have a way of remembering that. I just remember the equation, but I'm not really sure how else I could do it. You could remember via units, I suppose. You know the units up here are meters. The units on our speed are meters per second, and then units here are seconds. Well, meters per second multiplied by seconds is just going to be meters, because these 2 seconds are going to cancel each other out, and so therefore distance equals speed times time. Up to you. Okay, if distance is speed times time, then time is distance divided by speed. We're told the distance, 0.5 kilometers. However, we're remembering here that we have got speed in meters per second. In that case, we need to change one of our variables. We'll change this one into meters. We've got 500 meters divided by 330 meters per second, and a time of 1.515. Notice here, I'm keeping it as 4 significant figures for now, but I'm going to change it later. We're going to do the same for steel, and we calculate a 0.0833. Notice there that is 3 significant figures. Okay, we've got my 2 numbers. It's the time difference, delta, which is simply this one. Take away this one, we're left with 1.432. But at the end, tidy everything up and give it as 3 significant figures. So basically, we take a longer time. We take 1.43 seconds longer to go through the air than we do in steel. Okay. Another equation. Lots of equations in this paper. Lots of opportunities to get marks. We're told we've got a sound wave with a frequency. Okay, so let's get our pen out. Let's get highlighting things. Okay, you're told frequency. Write the letter for frequency there and make it easy on yourself. Okay, you're told the speed, v, and we're wanting to calculate the wavelength, lambda. Well, we know we've got 3 variables, 1, 2, 3, v equal f lambda. Again, remember the triangle, there's no other way of doing it. V, f, and lambda. We're told lambda is the ratio of v to f, and so therefore we've got a ratio here of about 0.66. Now that might seem like quite a lot, okay, but for sound waves, that's a completely fine value there. The wavelength of our sound waves is going to be very, very different. Last one, okay. Sound waves are longitudinal, okay, and visible light waves are transverse. Point. Sound waves are the only example of longitudinal waves that I have seen in CIE. So if you were asked for an example of a longitudinal wave, use sound waves. Okay, transverse waves, we've got different ones. We've got visible light, anything on the electromagnetic spectrum. So X-rays, gamma rays, radio waves, microwaves, they're all transverse. Water waves are also transverse. Okay, why? Well, in a transverse wave, the oscillation of our particles is at 90 degrees, or it's perpendicular to the wave direction. A wave is moving from left to right. Okay, my water is moving up and down and up and down. Yeah. Remember we did this with the springs, where we shook our spring from left to right, and then the wave traveled away from us. And that's what I've tried to draw in this picture here. I've drawn a spring which I've shaken up and down, and the wave is moving to the right. In a longitudinal wave, the oscillation is parallel to the wave direction. Okay, if we've got our oscillations like this, then if you notice my oscillations are left to right, and my total disturbance is moving in the same direction of those. And that's what I've tried to draw here. We've got longitudinal. These are compressions and rarefactions and compressions again. Okay, we've got the idea that these displacements, these oscillations are moving in the same or parallel to the wave direction.